Okay, so today I shall discuss a very important problem in filtering theory, namely quantum filtering. It is called the Belyaev-Kin filter. Belyaev-Kin filter, it is a non-commutative generalization. It is a non-commutative generalization of the classical Kushner-Kalyanpur stochastic nonlinear filter. Non-commutative generalization. Generalization of the Kushner-Kalyanpur filter. Nonlinear stochastic filter. So, it is based on you introducing non-commutative noise processes in the sense of Hudson and Parthasarathi satisfying the quantum Ito's formula. For example, the Hudson-Parthasarathi formalism is the natural way to treat noise to introduce noise in a quantum system, because if you so what happens is you have an open master equation which describes the dynamics of an open quantum system, and it is a non-unitary evolution, the master equation, but it can be dilated into a unitary evolution equation by introducing a bath and coupling the system to the bath. So what happens is, in the context of waveguides, what happens is that you have a waveguide like this or a cavity resonator, and within the cavity you have a field E and B, E and H, and outside the cavity you have a noisy field En and Hn. These are the noisy fields, and when you study the dynamics of the electromagnetic field within this cavity, you have to look at the Hamiltonian, total Hamiltonian of the cavity, which is the system and the bath. So the total Hamiltonian will be the sum of the system electric field and bath electric field, half integral d3r plus half integral H plus Hn square d3r. So it is the sum of the electrostatic field and the electric field and the magnetic field components. The two contribute to the total Hamiltonian of the system and bath. And if you look at just the system part alone and forget about the bath Hamiltonian, then it becomes, this can be written as, this total Hamiltonian can be written as 1/2, let us call E system and H system. So E system and H system. So it can be written as half Es square plus half Hs square integral d3r plus an interaction term which is equal to the inner product between the cross term Es dot En plus Hs dot Hn d3r. These cross terms correspond to, they define the coupling between the system variables and the bath variables. So if you express the system electromagnetic field in terms of system creation and annihilation operators using the vector potential formalism which I had discussed earlier in quantum field theory, and if you express the noise electric field and magnetic field in terms of quantum noise operators, namely the creation processes and annihilation, creation, conservation and annihilation process of Hudson and Parthasarathi, then the total Hamiltonian can be, after discretization, it can be represented as the total Hamiltonian of system and bath, system interacting with the bath, that can be expressed as half the system part, that is the system Hamiltonian part will be something like AK dagger AK into a frequency omega k summed over k. So this is the system Hamiltonian, and the bath Hamiltonian, the interaction component between the system Hamiltonian and between the system variables and the bath variables, it was represented by Es dot En, this cross term, and Hs dot Hn. So they will correspond to terms like summation AK into dak by dt or dam by dt into some function h of km of t and of r, the position, and you are integrating over all the positions. So they will not, the position variable will disappear, plus you will have terms like ak dagger dam t by dt dagger hkm bar to make it Hermitian, and you may have other terms like ak dagger into dam by dt into gkm, and you will have a and the Hermitian conjugate of this, which is ak into dam dagger by dt into GKM bar, where these are coefficients. In other words, the small ak and ak dagger, they define the electric and magnetic field of the system part. That is, the system electric field and system magnetic field can be expressed as linear combinations of the AKs and AK daggers, where AK and AK dagger they satisfy the bosonic commutation relations, namely AK comma AM is delta Km, AK comma AM dagger is delta Km, and AK comma AM is 0, which is equal to AK dagger comma AM dagger. So these are the bosonic commutation relations, whereas the creation and annihilation processes, they are noise processes. They describe the bath electric field and the bath magnetic field. So En and Hn, which are the bath electric field and bath magnetic field, can be expressed as superpositions of the time derivatives of the creation and annihilation processes, and you may also introduce conservation processes in the language of Hudson and Parthasarathy. So the cross terms are represented by such coupling terms. So the total Hamiltonian, if you write down Schrodinger's equation, you get dut by dt is equal to minus I ht into ut. This is the Schrodinger evolution operator, where ut is a unitary evolution operator, and ht consists of terms which I just mentioned. So since the derivatives of the creation and annihilation processes, they are not strictly defined, only the differentials are defined, dak dagger by dt. So you can bring the dt to this side, you can write this evolution equation as dut is equal to minus I ht ut dt, which can be written as minus I h plus p into dt plus L dA, so Lk dak dakt plus say L1k plus L2k dak dagger t plus sk d lambda kt, summed over all the k's here into ut. Essentially I multiply whenever I have a cross term which corresponds to the coupling between the system variables and the bath variables, then such coupling terms will be of form dam by dt into hkm. So if I bring the dt, multiply by dt on both sides, this will become a differential. This will become hkm ak dam. Actually it should be interpreted as the tensor product. Ak dam is the tensor product between ak and dam, because dam acts in the boson Fock space of the bath, whereas ak acts in the system Hilbert space, namely L2R plus, or you have L2R, several copies of L2R plus. So these Lk1, Lk2 and Sk, they are the system operators defined by such terms hkm into ak, hkm bar into ak dagger, then gkm into ak, and gkm bar into ak dagger. They are the system operators. So ideally speaking, when you write Lk1 into dakt, it means that Lk1 tensor damt, like this. So to show that the system Hilbert space and the bath Hilbert space are coupled through a tensor product. So this P is a quantum Ito correction term that is introduced to ensure unitary evolution. So this describes the evolution of the system interacting with the bath, and it's a unitary evolution. You can ensure that it is unitary by selecting these coefficients, so that ut dagger ut becomes I for all t, which amounts to saying that d of this quantity should be 0. So 0 should be du dagger into u plus u dagger into du plus du dagger into du. If you substitute for u dagger, du dagger and du, if you substitute for du dagger and du from that equation, let us say you have just a single creation and annihilation process in the bath, then you have a du is equal to minus I h plus p dt plus L dA, L1 dA plus L2 dA dagger plus s into d lambda multiplied by u. So that u dagger will be, the evolution equation for u dagger will be this u dagger into IH. So p is chosen to be Hermitian. So IH minus p, H and p are Hermitian. H is the Hamiltonian operator of the system alone. So H here corresponds to the system Hamiltonian alone, and these L1 dA, L2 dA dagger and S dA, they correspond to the interaction terms between the system electric field and the bath electric field and the system magnetic field and the bath magnetic field. So if you take the dagger of this side, of both sides, or the adjoint of both sides, this becomes plus L1 dagger dA dagger plus L2 dagger dA plus S dagger into d lambda multiplied by this. So, if you plug this into this equation and use the quantum Ito's formula in the form dA dagger is equal to dt, dA dagger dA is 0. This is the Hudson-Parthasarathi quantum Ito formula, and if you use, and it also implies d lambda square is d lambda, then dA d lambda is dA, and d lambda dA dagger is dA dagger. In the single, when you have just a single creation process, a single annihilation process and a single conservation process. So, if you use these identities and use the fact that system operators commute with Bath operators, then you will get a relationship between these operators L1, L2 and S, and that will be a condition, the defining condition for U to be a unitary evolution operator. It has been derived in standard textbooks, including the famous textbook by K.R. Parthasarathi, my dad, who introduced along with Professor R.L. Hudson this formalism of introducing noise into Schrodinger's equation in a correct way. So, if you take the quantum Ito's formula into account and substitute it in this equation, you will get a relationship between L1, L2 and S, these system operators. I do not want to derive that here. Now, and of course P also, P has to be introduced to ensure unitarity of the evolution. That is, if you put the condition that U is unitary, then you will get a relationship between P, L1, L2 and S. In the special case when there is no conservation process at all, when lambda is not taken into account, that means S is 0, then the equation acquires a very simple form, namely dUt equals minus I H plus LL dagger by 2 dt plus LdA minus L dagger dA dagger into ut. So, this LL dagger by 2 ensures that ut remains a unitary evolution. That is because you use the fact that when you compute du dagger du, due to the quantum Ito formula will give you a term like L dagger into L into dt, because dA dagger is dt, and when you substitute this into the equation du dagger u plus u dagger du plus du dagger du equal to 0, then this extra term which comes, it has to be cancelled out by a dt factor coming from added to the Hamiltonian. So, this ensures that the total evolution of the system and bath remains unitary. Now, if you look at the evolution of an observable, the system Hilbert space is denoted by H. Okay, that is the space in which the fields take the value, the fields within the cavity take the value. This is the system Hilbert space, and the bath Hilbert space is H. So that the bath actual space in which the bath operator has is the boson Fock space gamma SH, and the total Hilbert space is in which the system and noise operators act is this tensor product. So, I do not want to tell you what the boson Fock space is, but if you take it, just obtained by taking the direct sum of the symmetric tensor product of H of S n equals 0 to infinity, where n equal to Hs0 is equal to simply equal to the field of complex numbers. So, this corresponds to an indistinguishable bosonic particles. It is indistinguishable because you are using the system Hilbert space, you are using the symmetric tensor product S, and the fact that you are using the symmetric tensor product means the wave functions are symmetric, which means that you are dealing with bosons. On the other hand, if you use the antisymmetric tensor product, then it will be the fermion Fock space, but a successful theory of quantum stochastic calculus has been developed only for the boson Fock space. So, our processes AT and AT dagger, creation and annihilation and creation process and quantum and conservation processes, they act in the boson Fock space, whereas the small AK and AK daggers, they act in the system Hilbert space H. Right. Now, when you look at when you look at the total evolution, of the system and bath, you want to know what does an observable evolve like. So, X acts in the space H, acts as in the system Hilbert space as, for example, the electric field at a given point within the cavity or the magnetic field at a given point within the cavity. So that is a system operator, and you can view it as a operator acting in the Hilbert space of the system and the bath. So the tensor product of H and gamma SH. So where you introduce an identity operator. So under this, the Heisenberg evolution of this operator becomes ut dagger x tensor I into ut, or it can be simply written as ut dagger xi without, if you don't have any confusion about what the thing is, and you denote this by jtx. Since u is a unitary operator, it satisfies the equation jt of xy is equal to jtx jty, and jt of alpha x plus beta y is equal to alpha jtx plus beta jty. That means it is a homomorphism. It is a homomorphism between the algebras of observables on the system Hilbert space and the algebra of observables on the tensor product of the system Hilbert space and the bath space and the boson-Fock space of the bath. So it is a star unital homomorphism, and you can write down the equation satisfied by x. So if you denote this by x ut, after time t it evolves to xt, or this is jtx, then you can see that djtx will be equal to du dagger xu plus u dagger x du plus du dagger x du. And if you use the quantum Ito's formula, you can write this as jt of, whenever you have a u dagger comma u, there will be a term like, see it's like this, you are writing du equals minus I h plus p dt plus LdA minus L dagger plus plus LdA minus L dagger dA dagger. This should be skew Hermitian into ut. So when you multiply this du dagger, you will get a term like dA dagger into, of course, a u here. So it will be something like jt acting on some theta 0 x dt plus jt acting on theta 1 x dat plus jt acting on theta 2 x dat dagger plus, that is all. And you may have a lambda term also. I am just considering the case when you do not have any lambda, where theta 0, theta 1, theta 2 are linear operators acting in the space of observables, system space observables. For example, if you substitute, if you look at what du dagger x du gives, du dagger x into u gives, it gives a term like u dagger into ih minus p dt plus I am using LdA minus L dagger dA dagger. To ensure unitarity, it must be a skew Hermitian form, so it must be of this sort. That is because it must be a part of the Hamiltonian interaction Hamiltonian between the system and the bath. So here you get L dagger dA dagger minus LdA multiplied by x multiplied by u. So you get such a term, and when you look at the term x u into x into u dagger into x into du, that will give you a term minus I h plus p dt plus LdA minus L dagger dA dagger multiplied by x multiplied by sorry, this is u, so it should come out this way. Just one second, made a mistake here. So when you look at u dagger x du, this will be u dagger x into minus I h plus p dt plus LdA minus L dagger dA dagger multiplied by u. So if you combine these two terms, you will get a term like u dagger times I h comma x, which is the Heisenberg evolution part. When the observables evolve according to the Hamiltonian. So you will get one term like this into u into dt. So if there were no noise, then this is what will define the evolution, because you know Heisenberg's equation is dxt by dt is equal to I times h comma x. The other terms will correspond to noise processes, noise terms. So you will get a u dagger into p into u dagger x into p, then you will get a u dagger into p into x. Okay, so you will get terms like u dagger, p into x will give you minus of p into x plus x into p, like this you will get into u, where p is LL dagger by 2. Then you will get a term, then you will get a something into dA. What is that something into dA? It will be u dagger into L dagger into x into u into dA dagger, that comes from here. That is the coefficient of dA dagger here. The coefficient of dA dagger in this one is minus u dagger x L dagger dA dagger into u. Okay, u commutes with dA and dA dagger because dA peeps out of the tensor product space, so also dA dagger peeps out of the tensor product space. So the coefficient of dA dagger will be in effect u dagger into L dagger comma x, L dagger comma x into u, which will be and similarly the coefficient of dA will be, so this into dA dagger, and the coefficient of dA will be the conjugate, the Hermitian conjugate of this, namely this x comma L into u into dA. So you will get, so theta 1x will be simply x comma L, theta 2x will be L dagger comma x, and then you will get a dA dagger term. That is, if you look at the term du dagger x du, that will give you a term like u dagger into only a dA dagger will contribute to dt, that is one in the combination dA dagger. That means dA must occur here and dA dagger must occur in du, dA must occur in du dagger and dA dagger must occur in du. The coefficient of in du you have a term like LdA minus L dagger dA dagger. So the coefficient of dA is simply L, okay, L into x, here it is L dagger into du into u into dt. This will evaluate to this. All the other terms like dt dA dagger dt, they are all 0. So in effect what you will get, and you recalling that p into x plus x into p can be written as minus of L dagger x L dagger L x plus x into L dagger L by 2. You see that your theta 0x will be simply the Lindblad operator, namely I times h comma x minus half L dagger Lx plus x L dagger L minus L dagger minus 2 L dagger x into L. So this will be the Lindblad operator acting in the observable space. Likewise theta 1x we have discussed what theta 1x will look like. Theta 1x will be x comma L, like that. There will be linear operators acting in the space of observables, and if you put down all these things together you get the noisy Heisenberg equation as dJtx is equal to Jt of theta 0x dt plus Jt of theta 1x into dat plus Jt of theta 2x into dat dagger, and if there are lambda terms, that is if there are conservation process terms, then they will also appear, they will appear in the form of Jt of theta 3x into d lambda t, they will appear in this form, where theta 0, theta 1, theta 2, theta 3 are structure functions, they are called the structure functions. Theta 0x is a very important operator, it generates the quantum dynamical semigroup for the Lindblad equation, for the Glauber-Sudarshan Lindblad GKSL equation, Gorley-Kusakowski Sudarshan Lindblad equation. So this is of the form I times h0 comma x minus half L dagger Lx plus x times L dagger L minus 2L dagger XL. So it can also be written as L dagger, also this portion can be written as L dagger into L comma x plus x comma L dagger plus x comma L dagger into L. So if you look at the dual equation, of this, that is you look at how how the density of the joint density of the system and the bath evolve. So of course if there were no theta 1, theta 2, theta 3, then it will be the ordinary Heisenberg evolution equation, namely djtx by dt is equal to jt of I h comma x. The other terms can be interpreted as quantum noise. So if you look at the equation of the density, what is the density of the system and bath? It starts with the initial density of the system, tensor product the coherence with the coherent state of the bath. So phi u phi u. So phi u can be written as e to the power minus norm u square by 2 into EU, where EU are the exponential vectors introduced by Hudson and Parthasarathi. So after time t, what is the evolution of the system and bath? The joint density of the system and bath becomes ut into rho s 0 tensor phi u phi u phi u phi u. A coherent state you are using because coherent state is a definite eigenstate for the electric field components. That means if you look at AT acting on EU, the exponential vector, that will give you simply integral us ds from 0 to t multiplied by EU, or you can write this equation as dAT acting on EU is equal to ut dt multiplied by EU. So the exponential vectors or equivalently the coherent vectors are eigenstates of the electric positive frequency components of the electric field, because the creation of the annihilation operators, they define the magnetic vector potential for the noisy bath as we had seen earlier. And so this is the equation of evolution of the system and bath. And if you take the partial trace ut into ut dagger, if you take the partial trace of this, you get the system state evolution at time t, namely ut trace of 2 means trace over the second component, which is the bath, ut into rho s 0 tensor phi u phi u. Phi u is a normalized version of the exponential vector into ut dagger. And you can, if you write down the differential equation satisfied by rho st by using the formula for dut given by Hudson Parthasarathi equation and dut dagger, if you use this, then you will get the GCSL equation when the bath is in the coherent state u. So u is a vector in the Hilbert space H, and remember that gamma sh is the boson Fock space for the system, for the bath space observables. So EU becomes a vector in the boson Fock space, and EU comma EV becomes e to the power u comma v. If you write down the formula for u essentially the exponential vector is nothing but 1 plus u tensor 1 by factorial 2 direct sum root factorial 1 plus u tensor 2 by root 2 factorial plus etc. So you can write the exponential vector as 1 plus the direct sum n greater than or equal to 1 u tensor n divided by root factorial n, and that gives you the relation that EU comma EV, the inner product between EU and EV is e power u comma v. So if you write down the dynamical equation for rho st, you can do it in various ways. First you can do it by taking the dual relation satisfied by ut dagger, the dual equation of the Heisenberg evolution equation, but it is easier to take the derivative in this way, and what will happen is that you will get, if you use the fact that dAT acts on phi u to give ut dt into phi u, that is, use the fact that the coherent vectors are eigenstates of the annihilation operator, then you will end up with the Gorini GCSL equation, also called the Gorini-Kosakowski-Sudarshan-Lindblad master equation for an open quantum system, which is of the form d rho s t by dt is equal to minus I h0 comma rho t, rho s t. This is the normal Schrodinger equation or the Liouville von Neumann equation plus theta acting on rho st, where in the special case when the coherent state of the bath is the vacuum coherent state, u is the vacuum coherent state, then theta into rho st becomes the dual of theta 0 star. Theta 0 acted on x, as we saw, to give I times h comma x and so on. So, I omit the Hamiltonian part, I look at only the noise part in theta 0. So, the noise part in theta 0, if I call it as theta 0 x n, then that is minus half, the dual is L dagger L x, L dagger L x plus x L dagger L minus 2 L dagger x L. If you take the dual of theta 0 n, you will get theta, So, theta 0 n star is simply theta. So, you can write that as, how do you calculate the dual of theta 0 n? Theta 0 n x acting on rho must be equal to trace of x times theta 0 n star acting on rho, which is equal to trace of x times that theta 0, which I call here. So, I write it as theta into rho. Theta 0 n star is the dual of theta 0 n star is the dual of theta 0 n. So, this can be written as trace of minus half trace of L dagger L x plus x L dagger L minus 2 L dagger XL multiplied by rho, which can be rearranged to write using trace of AB is trace of BA. This becomes trace of x times rho L dagger L plus x times plus L dagger L x L dagger L rho minus, of course I am using rho s is the system space observable, system space density matrix, minus 2 L rho L dagger. So, this becomes the dual, this can be written as, so it follows that theta 0 n star acting on rho s is simply given by rho L dagger L minus half rho L dagger L plus L dagger L rho minus 2 L rho L dagger, and its trace is 0 as it should be, so that it preserves the trace, the dynamics preserves the trace rho is equal to 1, total probability. So, the Gorini-Sudarshan-Lindblad equation in the special case when u is 0 acquires a very simple form. It is d rho s t by dt is equal to minus I h, I write h for h0, right. H is the system space Hamiltonian, comma rho s t, system of Hamiltonian. In the special case of the cavity resonator, it is the Hamiltonian of the field within the cavity, which is of the form summation omega k a k dagger a k, that is all. If you had fermions, then you would have to add the Dirac part, namely creation, annihilation, or the Hamiltonian of the Dirac part, which is a quadratic forming the fermion creation and annihilation operators. I am just avoiding that right now. So, minus half L dagger L rho s plus rho s L dagger L minus 2 L rho s L dagger. You can check the sign by taking the trace of this vanishes. So, in particular, if you take the trace on both sides, you get trace of rho s t is equal to trace of this is trace of AB minus B, trace of AB minus BA is 0, and trace of this is also 0 because trace of AB minus BA is 0, which is the correct equation, namely trace of rho s t must be 1 for all t if it is 1 at time t equal to 0. So, this is called the GCSL equation. This was derived much before the advent of the Hudson-Parthasarathi quantum stochastic calculus. It was derived from purely heuristic considerations of the evolution of Heisenberg evolution, the Schrodinger evolution. That is, if you look at d rho s t by dt, suppose you write the Schrodinger evolution equation in the absence of noise, where h t contains the noise term. So, it is of this form. So, where h t is the Hamiltonian of the system alone. So, you could write this as rho s of t plus tau is equal to minus I integral t to t plus tau hs comma rho s ds plus rho s of t for small tau. Then I replace rho s t by again the same equation. So, I will get something like this integral will become something like a double integral h of s1 comma h of s2 comma rho s, and the rho s is approximated by rho t. So, rho s at t you get this approximate equation ds1 ds2, where s2 goes from 0 to s, or s2 goes from t to s, s1, and s1 is less than t plus tau, s1 is less than t plus tau, and s2 is greater than or equal to t. So, by making approximations to this equation and taking the averages, you can get the Lindblad equation using the fact that H1 comma H2 comma rho s for two operators, these are the form H1, this is the form H1 into H2 rho s minus rho s H2 minus H2 rho s minus rho s H2 into H1, which is equal to H1 H2 rho s okay, plus rho s H2 H1 plus rho s H2 H1 minus H1 rho s H2 minus H1 rho s H2 minus H2 rho s H1. So if you take the averages over H1, assuming H to be of the form some H0 plus a noise par delta H, then you will get the Lindblad equation by making this approximation. It was derived in this way earlier by Gorini, Kosakowski, Sudarshan and Lindblad, but it was Hudson and Parthasarathy who gave a rigorous explanation of how this can be derived using using a unitary evolution of the system and bath, so that there is no coupling from outside over to the system and the bath. It always a unitary evolution, and then you take a trace over of the bath variables to arrive at the Sudarshan-Lindblad equation. When the coherent state u is non-zero, then of course in the Lindblad operators u will also come, there will be a Lindblad term. Anyway, our aim is not that. Our aim today is to present a filtering theory. Our aim today is to present a filtering theory of Belyaukin, filtering theory of BP Belyaukin. So what exactly is filtering? You have a system here, you have an atom, okay, the atom with an electron around it, this is the atom, this is the system. In our case the system is the cavity electric field, and you want to measure things about the system. So if you, one way to measure things about the system is to directly shine light on it and try to measure the system, but you know the Heisenberg uncertainty principle that it will destroy the system dynamics once you shine light on it, once you try to shine light on it. So you look at a special sort of a light signal, a special sort of an electromagnetic signal, you shine it upon the atom, and this light gets perturbed, it gets scattered in a different way, and you call this as the input measurement. Input light is input light process, I call it as YIT, and the perturbed light process I call as YOT. This is the output light, it gets perturbed with the system. The system satisfies the Hudson-Parthasarathy evolution equation, right, in the presence of bath variables, and the perturbing light or perturbing electromagnetic signal which falls on this atom and gets perturbed to Y0T, that falls in the boson-Fock space of the bath because it is a noisy process. So your Hudson-Parthasarathy equation for the evolution operator is minus I H plus P dt plus L dA minus L dagger dA dagger into UT, and when light gets perturbed by this, then the system is trying to perturb this light. So the output measurement will be of the form YOT, which is UT dagger YIT into UT, where YIT should be interpreted as a process in the bath space, that means I tensor YIT. I corresponds to the identity of the system Hilbert space, namely on H, and YIT falls in the boson-Fock space, namely gamma SH. So when light gets perturbed, you observe YOT, but you use what is called a non-demolition measurement. Non-demolition measurement. Non-demolition measurement means a measurement YOT which commutes with the future evolution of the system state, of the system observable under noisy dynamics, so that it does not disturb the system. You just measure YOT, and from that you are able to infer something about the system. That means this must commute with the, not only with itself, it must commute, they should form an abelian family of operators, but they should also commute with the future value of the system state, so that they do not disturb the system, and Heisenberg uncertainty principle will not apply for commuting operators. It will you are able to measure the system future system state, and from you are able to estimate the future system observable from the non-demolition measurement YOT. So in other words, I require that YOT comma JTX I require that YOT comma JSX for X is system observable. This should be 0 for S greater than or equal to T, and also that YOT comma YOS, this is 0 for all T and S, so that I can talk of a joint probability density of JSX, the future system state, the family of measurements, output measurements YOT up to time S, I can talk of a joint density of this, which means that I can talk of a conditional expectation of the system state at time t given all the output measurement up to time t. I am able to talk of this conditional expectation, and this I call as pi tx, where x is a system observable, that is x belongs to a linear Hermitian, the space of linear operators on the system Hilbert space LH. So I am able to give meaning to this conditional expectation. So how do you derive an evolution equation for pi tx? It is very simple. First, how to define a non-demolition measurement? How do we define a non-demolition measurement? So you start with, for example, yit is equal to C1 times AT plus C1 bar times AT dagger, so that it becomes Hermitian, plus C2 times, you can have a lambda t, you can have a conservation process also to make it, keep it more general. And if you look at this family forms an abelian family. So you can see that yit comma yis is equal to 0 for all t and s. That is because C1 dA plus C1 bar dA dagger plus C2 d lambda, this commutes at different times. If you evaluate this at time t and you evaluate it at time s, the same thing evaluated at time s, they will commute with each other. That is because dA, it peeps out of the tensor product. dAt multiplied by dAs is equal to 0 for t not equal to s. Similarly, dAt multiplied by d lambda s, this is 0 for t not equal to s. Similarly, dAt multiplied by dA dagger s, this is also 0 for s not t not equal to s. So they commute with each other. So this forms an input. The input family of measurements is an abelian family, namely yit comma yis is 0 for t not equal to s, it forms an abelian family. Now if you look at, if you take some t greater than t, suppose you take some t greater than t and you define ut yit into ut dagger. Suppose I consider this expression where t, capital T is greater than t. If I take d of this, the differential of this with time, then I will get various terms, right. With respect to capital T I am taking the differential. This will give you dut multiplied by yit multiplied by ut dagger plus ut multiplied by yit multiplied by ut dagger plus dut multiplied by yit multiplied by dut dagger. And you see, because ut is already an evolution operator, unitary evolution operator, because I have already adjusted the Lindblad parameters L, L1, L2 and S, so that it defines a unitary evolution. And since this belongs to a boson-Fock space, all the members of dut, all the members of dut will commute with yit, right. All the members of dut will commute with yit, right, because dut consists of what? It consists of things like hdt, pdt, then it consists of things like ldat, then L dagger, L1 dat, L2 dat dagger, sd lambda t, and at the point capital T. So it will consist of terms like dut will consist of terms like h into dt, then p at t into dt, then L at t into dat, then L at t dagger into dat dagger, or L1 into L1t into L1t, L2t into dat dagger, then S at time t into d lambda t, and all these system operators commute with the yits, because yits take values in the boson, operate in the boson-Fock space alone, right. So dat will also commute with yit and dat dagger will also commute with yit. That is because capital T is greater than t. So you can see that dat will commute with yit, this is 0, then dat dagger, that will also commute with yit. Likewise d lambda t, that will also commute with yit for all t greater than t, because yit takes values in this boson-Fock space up to time t. you see YIT acts in the boson Fock space gamma s h up to time t. So you are using a continuous tensor product to define this. It is an adapted process, and DAT is independent of HT. That is DAT, you can look at dA capital T acting on, what you can say is that dA capital T acting on an exponential vector will act only on the component dt of ut. So it will be simply equal to ut into EU, ut dt multiplied by EU. Whereas on the other hand, if you take YIT acting on EU, since it is an adapted process, this is same as YIT acting on EU up to time t, tensor product EU from t to infinity. So it will not touch the part after capital time t, the part after capital time, after small time t, it will not touch that part, YIT will not touch that part. So it will commute with DAT. That means that what we have deduced is that if you look at the output, noise process UT dagger UT, I call this as YOT, then you see that let us forget about this YOT, you see that D of this with respect to t is 0. That is because DUT and DUT dagger consists of terms like DAT, DAT dagger, d lambda t, all of which commute with YIT, because YIT is an adapted process. It operates only on the exponential vectors up to time t, whereas DAT will act on the exponential vector for u after time small t, because t is assumed to be greater than t. So it will commute, right. So okay, so it is clear that it will commute. So what you can say is that if you define YIT, if you define YIT to be equal to UT dagger YIT into UT, then this will be the same as UT dagger into YIT multiplied by UT for all t greater than or equal to t, because d of this with respect to capital T is 0. So what does it mean? If you look at, for example, JTX is what? It is UT dagger multiplied by x multiplied by UT. So if you look at JTX multiplied by YIT comma YIT for t greater than t, then this is nothing but UT dagger x UT comma UT dagger YIT UT, right, which is the same as UT, since u is unitary, UT dagger x comma YIT multiplied by UT, which is 0 because x comma YIT is 0, x is a system operator, y acts purely in the boson Fock space, so this is 0. So you can see that these two commute, JTX commutes with this with YOT. So what I am trying to say is the following: you are defined JTX to be UT dagger x into UT, and you have defined YOT to be UT dagger into YIT into UT, and we have shown that this is the same as UT dagger into YIT into UT for t greater than t. So from these two equations it follows that JTX comma YOT, this is 0 for all t greater than or equal to t, because UT is a unitary operator, right. If I use these two expressions, if I use equation 1 and equation 2 and use the fact that UT dagger is identity. So YOT forms indeed a non-demolition output process which can be used to construct conditional expectations of the state at time t given all the measurements up to time t. Let us see how I will give you a proof of the filter based on an analysis by John Gow and Kostler in a very famous paper in which they simplified Belyavkin's proof considerably. So let us see how to go about doing it. So you define a filter pi tx to be expected value of JTX given eta OT. right, where eta OT is the algebra, von Neumann algebra generated by the observables YOS output measurements up to time t. And since this is a, so pi t, it is clear that pi tx will commute with for all values of small t, because pi tx will be measurable with respect to this von Neumann algebra, and this is an abelian family, right. You see that YOS comma YOS prime is 0 for all S and S prime, because YOS can be written as simply UT into YIS into UT dagger YIS into UT, and YOS can be written as UT dagger into YIS prime into UT, provided T is greater than S and S prime. So I can write it in this way, and this is the same as UT dagger into YIS comma YIS prime into UT, and YIS commutes with YIS prime, because YIS has been taken to be of the form C1A S plus C1 dagger C1 bar C1 bar AS dagger plus C2 lambda S. So you can see that this forms an abelian family. So the output measurement process also forms an abelian family. So you can when you define the conditional expectation of the observable at time t, evolving observable at time t, this takes values in the space of operators on both on the tensor product of the system Hilbert space and the boson Fock space. So if I define this to be eta OT, then you see that pi tx is measurable with respect to eta OT, so it forms a commuting family. So you expect that pi tx will satisfy a stochastic differential equation, a classical stochastic differential equation of the form ftx dt plus gtx dyot, where yot forms the measurement sigma algebra, that is YOS S less than t less than or equal to t, the algebra generated by this is precisely eta OT, and ftx is measurable with respect to eta OT, and gtx is also measurable with respect to eta OT, because it is a conditional expectation, and this conditional expectation is taken in the coherent state of the bath phi u. So this is a classical filter. And what is YOT? See, YOT, you are taking dyot as C1 into DAT plus C1 bar into DAT dagger, right. So dyot square is simply equal to mod C1 square dt by quantum Ito's formula. So higher than dyot terms won't occur, but if you have a Poisson term, in dyot, that is if you have something like C2 into d lambda t, then of course dyo square, dyo cube, they will all contribute, in which case you have to modify the filter. If you have a measurement of the form YIT, YIT is equal to C1 into AT plus C1 bar into AT dagger plus C2 into lambda t, or more generally you can take dyit to be equal to C1t into DAT plus C1 bar t into DAT dagger plus C2t into d lambda t. So that YIT is an integral of this, where C1 and C2 are C1 is a complex valued function of time and C2t is a real valued function of time. In that case you will see that YOT, dyot square, dyot power n will be non-zero for all n equals 1, 2 and so on. That is because if you used a quantum Ito's formula DAT into d lambda t, that is DAT, and d lambda t into dA dagger t is DAT dagger, and d lambda t square is d lambda t. So if you use it, you will see that dyot all powers of n will contribute, and if you take all those powers of n into consideration, your Belyaevkin filter, the filter equation should be something like d pi tx is equal to ftx plus summation k greater than or equal to 1 gtkx into dyot power k. Only when there is no conservation process it will terminate at k equal to 1. So this should be the general form of the of the filter. So let us see how to compute ft and gtk, how to compute these filter coefficients. So they are computed by using Gauss formalism of the orthogonality principle, or also called the reference probability approach. Orthogonality principle, which Gauss has also called the reference probability approach. It is very simple. Jt is the state estimate and pi t is the Jt is the state at time t, pi tx is the state estimate, and you know from basic orthogonality principle in estimation theory that this should be orthogonal to the conditional, pi tx is the conditional expectation of jtx given the measurement sigma field up to time t. So this should be orthogonal to all the measurement observables up to time t. So you choose a particular sort of observable, you choose an observable, let us call this as dct, let us call it as dct given by ct into ft into dyot, and c0 equal to 1, satisfying this stochastic differential equation where ft is simply a real valued or a complex valued function of time, right. So it is clear by iteration that ct can be expressed as, so ct belongs to the sigma algebra generated by the measurements up to time t, that means ct can be expressed as a function of the output measurement algebra or the output measurements yot up to time t. In other words, ct can be written as some function of yos as less than or equal to t by iteration, by iteratively solving this equation it will come out to be a Volterra series solution or a chaos expansion in dyo. Okay. If you have of course both conservation, a conservation process also appearing in the Hudson-Parthasarathi equation and also in the measurement equation, then you should replace this by dct equals summation fkt into dyot power k equals 1 to infinity multiplied by ct. So this will give you a general form of ct. So you used a fact that jtx minus pi tx is orthogonal to eta ot, which means that the conditional expectation in the coherent state phi u, in the coherent state phi u multiplied by ct, this should be 0. That is the, by definition the conditional expectation is the best minimum, is the minimum mean square estimate of the variable, minimum mean square estimate of the variable. So it should be, the error should be orthogonal to the data, this is the estimation error and this should be orthogonal to the data. So if you take d of this equation, what do you get? Gauss' idea is to take d of this equation and take d with respect to t and this is, put that as 0. So what do you get? You get expected value of d jtx minus d pi tx multiplied by ct, okay, plus expected value of jtx minus d minus pi tx multiplied by dct plus expected value of d jtx minus d pi tx multiplied by dct. Product of these three conditional expectation, this should be 0. I have just used the fact that for two variables a and b, dab is nothing but dA into b plus a into db plus dA db. This is the standard formula just obtained by replacing a by a plus dA and b by b plus db, and taking the difference with a and b, ab. So you will get this equation in the general case. So if you now substitute for djt and you see once you take this equation and put it as 0, I am free to choose my fk's to be arbitrary in this equation. For example, if I note how I have defined my ct, I have defined my ct to satisfy a classical stochastic differential equation of the form fkt dyot power k into ct, k greater than or equal to 1. So if I substitute for dct into this equation, I will get fk terms coming in these two equations. I can put all those fk's to be 0 at that time t to get that this is equal to 0, right. So this equation will imply two equations. It will imply that expected value of djtx minus d pi t x. Separately it will imply Ct equal to 0. It will imply this by putting fkt as 0, and 2 it will imply expected value of djtx minus d pi tx multiplied by dct plus expected value of jtx minus pi tx multiplied by dct. Okay, this is also 0. It will imply both of these equations separately, and this equation will of course imply that the conditional expectation of this error given eta ot is 0, because Ct can be an arbitrary variable in eta ot. Ct can be chosen to be an arbitrary variable in eta ot. So it will imply that the conditional expectation of this is 0. Here if I substitute dct, so the first equation will imply that expected value of djtx minus d pi tx given eta ot, this is 0. It will imply that this is 0, and the second equation will imply that djtx minus d pi tx. Now here I have a dct. The dct is nothing but fkt into dyot power k, fkt dyot power k into ct. So I am free to choose fk as non-zero or fk as 1 and all the other fjs as 0. So it will imply that this into dyot power k given eta ot. I am allowed to choose a particular fk as 1 and all the other yks as 0, and if you multiply by ct, since ct is arbitrary, I can take a conditional expectation given eta ot plus expected value of jtx minus pi tx into dyot. Here dyot will become dyot power k given eta ot. So the sum of these two conditional expectations is 0 for all k equals 1, 2 and so on, right. So this will these two equations, from these two equations I can calculate all the gks. Here I am assuming the filter to be of the form d pi tx is equal to ftx dt plus summation k greater than 1 gktx into dyot power k. So for example, if you want to evaluate the first one, what will I do? You put djtx. Djtx is nothing but jt of theta 0 x dt plus jt of theta 1 x into dat plus jt of theta 2 x into dat dagger plus jt of theta 3 x into d lambda t. I get these two terms minus pi t minus d pi t. D pi t is nothing but ftx dt minus summation gm tx dyo t power m. So the product of this, the sum over all this given eta ot, this is 0. So what will it give? Jt of theta ox will give you pi t of theta ox, theta 0 x into dt plus jt of theta 1 x into dat, expected value of dat. What is expected? What is the conditional expectation of dat given what is the conditional expectation of dat given eta ot in the coherent state phi u? Dat is simply independent of the boson of the dat is simply independent of eta ot, because eta ot falls in the Fock space of the up to time t, in the Fock space up to time t. So dat is independent of this, so this will be simply ut dt. Similarly, expected value of dat dagger given eta ot, that will be ut bar into dt, and likewise expected value of d lambda t given eta ot, that will be mod ut square dt. So you will get all terms here, right. You will get pi t of theta ox, theta 0 x plus pi t of theta 1 x multiplied by ut plus pi t of theta 2x, pi t of theta 2x into dit dagger, which will give you u bar t dt, and then plus theta 3x, that will give you pi t of theta 3x into d lambda t, which is mod ut square minus ftx dt minus summation gmt at x summed over all m into expected value of dy ot power m given eta ot, that is 0. So, you will get a relationship for ft between ft and gt. So, you have to evaluate dy ot power m given eta ot, you have to evaluate dy ot power m given eta ot. I am considering the general case in which the Hudson-Parthasarathi equation contains, apart from creation, annihilation, noise process, also a conservation noise process, and the non-demolition measurement also contains a creation, annihilation and conservation process. So, you have to evaluate this in order to get a relation between, a linear relation you will get, you are getting a linear relation between ftx and gmtx in terms of these values. So, how do you calculate dy ot power m? It is not an easy job. In the special case when there is no conservation process, it is very simple. Simply expected value of you will deal with only m equal to 1 in that case. In that case, expected value of dy ot given eta ot is easily calculated. How do you calculate it? Simply use the fact that yot is equal to ut dagger into yit into ut. So, dyo is equal to du dagger into dyi into u plus u dagger into dyi into du plus dyi plus du dagger into yi into du dagger. Now, you see these terms, if you look at this into dy, right. If you look at plus of course it will involve the first order terms also, du dagger into yi into u plus u dagger into yi into du. If you look at these terms, du dagger yi du dagger yi u dagger yi du, this will cancel out because u is unitary, and the terms in du dagger they all commute with yi at time t. So, this will cancel, these terms will cancel, you will get just these terms. So, you have to evaluate du dagger dyi du. How do you evaluate that? Du dagger dyi into u, simply substitute. For example, you want to calculate du dagger into dyi into u, and you also have to calculate u dagger into dyi into du. So, u dagger is nothing but u dagger into du dagger into ih minus p dt. Okay, since only a quadratic, since you are multiplying du dagger with two differentials, only this will be non-zero only when du dagger it will be non-zero only when you use the term in du dagger involving dA, and here you should get dA dagger in dyi, or here you should get dA and here you should get d lambda, or here you should get d lambda and here you should get d lambda. Only these products will contribute a non-zero term to this Ito's factor, to this product term, product of two differentials. So, u dagger, these dt terms will not contribute. So, if you look at du dagger, this is nothing but L1 dagger dA dagger, that will not contribute, L2 dagger dA, that will contribute. I am assuming the Hudson-Parthasarathi equation to be of the form minus I h plus p dt plus L1 dA plus L2 dA dagger plus S d lambda into u. So, it will contribute a term when you put L2 dagger into dA, L2 dagger dA plus S dagger into d lambda. Okay, these are the terms in du which should appear here, and for getting a non-zero product term, and in dyi what are the terms? It is C1 into dA, that will not contribute, it will be C1 bar into dA dagger which will contribute, plus C2 into d lambda which will contribute into u. So, this will be equal to simply u dagger times Now here you have C1 bar into dA dagger is dt. So it is C1 bar L2 dagger into dt. Okay, C1 bar into L2 dagger into dt plus here you can get a dA into d lambda that can come. So it will give you C2 dA into d lambda is dA, right, dA d lambda is dA. So this will be C2 multiplied by dA, C2 dA d lambda is dA into L2 dagger, okay, this into L2 dagger into dA. Term will come like that. Then d lambda into d lambda is d lambda. So that will give you plus C2 S dagger d lambda multiplied by u, right. So it will give you a term of this sort, and the other term is u dagger dyi du can be obtained by just taking the Hermitian conjugate of this. So this will give you what? It will give you Jt of C1 bar L2 into dt, C1 bar L2 into dt plus C2 into or Jt of C2 L2 dagger into dA plus Jt of C2 S dagger into d lambda. In the case when d lambda is, when there is no conservation noise term, that is S is 0, it will give you only a dt term and a dA term, right, it will give you only a dt term and a dA term. So in the general case and of course the Hermitian conjugate of this. So in the general case what you will have is that dyo will be of the form Jt of some m1 into dt plus Jt of m2 into dA plus Jt of m3 into dA dagger plus Jt of m4 into d lambda. So you will have 4 terms where m1, m2, m3, m4 are system space operators, that is they act in the system Hilbert space math frac H. Math frac H is the latex command used to write down this expression for H. In the special case when there is no conservation process, then it is simple, dyot will be simply of the form Jt of what will happen when there is no conservation process term, that means yit, there is no conservation process term either in the Hudson-Parthasarathi equation or in the measurement model, in which case you are having only C times At plus C bar At dagger. So in that case dyot will be simply dyit plus dut dagger into dyi t into u t plus ut dagger into dyit into dut, which will be simply dyit plus ut dagger. So I am assuming in this case that ut has evolution equation minus I h plus p dt plus L dA minus L dagger dA dagger. In that case that du dagger dyi will give you a term like L dA multiplied by du dagger minus L dA multiplied by C. So plus Jt times minus Jt times C into L dagger L C2 C into L. So here you have du dagger will give L into dA dagger, which is C bar dA dagger C bar L plus C L dagger dt, C into this into dt. So you can see that in this case when there is no conservation process either in the Hudson-Parthasarathi equation or in the measurement model, output measurement differential is nothing but a system operator being measured after passing through the Hudson-Parthasarathi noisy Schrodinger equation, namely this observable is being measured minus of C bar L plus C L dagger. You are measuring this observable with noise dyit. So it becomes the usual Kushner-Kalyanpur model of the measurement model, in this special case. Otherwise, in the general case you get, apart from these terms dA dagger, other terms come. So it is very simple to calculate in this case. So but in the general case what will happen is that when conservation noise process is also present, conservation processes are also present in the Hudson-Parthasarathi equation as well as in the measurement model. Your dYOT will be of the form JT of m0 into dt plus JT of m1 into dA plus JT of m2 into dA dagger plus JT of m3 into d lambda, and then you have to calculate dYOT power k, dYOT power m given eta OT, given the measurement of algebra up to time. To calculate dYOT, and it is not simple. So you do it by recursion. You assume that dYOT power n power m is of the form JT of m0n dt plus JT of m1n into dA plus JT of m2n into dA dagger plus J3 of m3n into d lambda for n greater than or equal to 1, and you apply the recursion. You apply the fact that dYO power n plus power m plus 1 is equal to dYOT multiplied by dYO power m, and equate coefficients of dt, dA, dA dagger and d lambda to get all these matrices, all these system operators m0n, m1n, m2n, m3n. For example, if you write down dYO n plus 1, what is it? It is JT m0 n plus 1 dt plus JT of m1 n plus 1 into dA plus JT of m2 n plus 1 into dA dagger plus JT of m3 n plus 1 into d lambda, and this must be equal to JT of m0 into dt plus JT of m1 into dA plus JT of m2 into dA dagger plus JT of m3 into d lambda multiplied by JT of m0n into dt plus JT of m1n into dA plus JT of m2n into dA dagger plus JT of m3n into d lambda. So if you equate coefficients of dt, what do you get? m0 n plus 1, m0 n plus 1 equals, equate coefficients of dt can come when you have a dA here and a dA dagger here. So it will be m1 JT of m1 multiplied by JT of m2n, which is JT of m1 m2n. So if you use the fact that JT of u into JT of v for system observables is JT of uv, and equate the coefficients of dt, you get m1 times m2n. This is m1 times m2n for all n. If you equate the coefficients of dA, what do you get? You get m1 n plus 1 is equal to, how can A come? It can come only when you have a dA into d lambda, right. So here you have m1 into here you have m1 into n3n, right, m1 into m3n. If you equate the coefficients of dA dagger, what do you get? m2 n plus 1 is equal to m2 n plus 1. You can have a dA dagger when you have a d lambda here, when you have a d lambda on the left side and you have a dA dagger on the right side. That means you have m3 into m2n, m3 into m2n. And finally, if you equate the coefficients of lambda on both sides, you get m3 n plus 1, d lambda square is d lambda. So here you get m3 into m3n, m3 into m3n. It is very easy to solve these recursive equations with the initial condition that m20 is, that m10 is m1, m20 is m2, m30 is, sorry, m21. You just solve these conditions for n greater than or equal to 1 with the initial condition that m1n is m1, m21 is m2, m3n is m31 is m3, and m01 is m0. If you solve these recursive equations, you get the formula for dYOT power n. So, in that case what will happen? To calculate expected value of dy ot power m given eta ot, this is nothing but expected value of jt of m0 m into dt plus jt of m1 m into dA to dat plus jt of m2 m into dat dagger plus jt of m3 m into d lambda t given eta ot, and you can see that clearly in the coherent state. So, this is nothing but pi t of m0 m plus pi t of m1 m. Okay, this will not get affected. The conditional expectation of this portion will come out, dat will come out of this conditional expectation once you condition on eta ot, and then you take the expectation in the coherent state. So, first you take the conditional expectation given eta ot, so this will become ut, expected value of dat given eta ot is nothing but ut dt, whereas jtm 1m will come out of the conditional expectation. So, right, because you can factor out the because of the isomorphism. You see, if you look at the exponential vector u, then this is the same as the exponential vector up to time t, tensor product the exponential vector after time t. Because of this factorization you are able to write this down in this form, plus pi t of m2m into ut bar plus pi t of m3m into mod ut square, right. So, if you use this fact, you get, and all this pi t m0 m, pi t m1m, they are all measurable with respect to the output measurement algebra up to time t. So, they all commute with each other. So, in this way you are able to evaluate everything. If you want to evaluate the other term, for example, you want to evaluate expected value of djt x minus d pi t x into dct, you want to evaluate this quantity, then what will you do? You will again substitute for jtx, you will put jt of theta 0 x dt plus, okay, the only terms which will come into the picture when you are the dt terms will not come into the picture at all, right, because dt multiplied by any differential will give you 0. So, it will start with either this can contain a dA or a dA or a d lambda, this term, and here, so you can have a dA or a d lambda coming from the first term, and here you can have either a dA dagger or a d lambda in this. You cannot have a dA here because anything into dA is 0, any differential into dA is 0. So, you pick out only the dA and d lambda terms here, which are jt of theta 1x into dA plus jt of theta 3x into d lambda minus d pi tx. So, d pi tx was what? D pi tx was minus ftx dt, that dt will not come here. So, minus sigma g k tx multiplied by dy ot power k greater than or equal to 1 multiplied by dctx. dctx will give you an fk. So, you can choose a dy ot power m here into fm. I can put that fm as 1 and all the other m's as 0. So, this given eta ot, right, this is equal to 0. So, I will get this sort of an equation, and I can calculate dy ot power k into dy ot power m. That will give you a term of dy ot power k plus m, and you are taking the conditional expectation of this given eta ot, and I have already derived a formula for this in terms of the pi t. So, you see, you will get another, for example, if you want to calculate jt of theta 1x into dA given eta ot, that the first term is simply pi t of theta 1x into ut into dt, right, because expected value of jt theta 1x given eta ot is pi t of theta 1x dt, and expected value of dA given eta ot is simply ut dt. So, I will get another linear relation between the gkt's and the Fks. So I easily get the Bilyavkin filter in the general case, in the most general case when all types of noise, mixture noises, that is Gaussian and Poisson, quantum Gaussian and quantum Poisson noise are present in the measurement model as well as in the state model of Hudson and Parthasarathy. All these things simplify drastically when you do not have any conservation noise in the Hudson Parthasarathy equation and you do not have anything in the no conservation noise in the measurement model. That is, you are taking a special case in which dyot is equal to dyot will be of the form dyit minus jt c bar l plus cl dagger dt with yit given by c times at plus c bar at dagger. So it will simplify in this case drastically. In that case higher powers of dyot will not contribute, dyot power m will be 0 for all m greater than or equal to 2. So in that case the filter becomes simply d pi tx is equal to ftx dt plus gtx into dyot and I get a very simplified form. So I will get, for example, an equation like djtx minus d pi tx multiplied by dct. So that will give you dyot given eta ot, that will give you 0 and this will give you this is the first equation that will give you expected value of jt of theta 0x. Okay, this is not 0, you are taking this given this is 0, right. So this will give you jt of theta 0x, jt of theta, this will give you simply the equation pi t of theta 0x plus pi t of theta 1x into ut plus pi t of theta 2x into ut bar minus d pi t. So minus ftx into dt minus gtx into expected value of, okay, what is the second term in d pi tx? It is gtx into dyot and we are taking the conditional expectation of this given eta ot, right. So gtx will come out because it is measurable with respect to eta ot and expected value of dyot given eta o can be found out very easily if you use the fact that dyot is equal to dyit minus jt of c bar l plus cl dagger dt. So you see that expected value of dyot given eta ot, this conditional expectation, expected value of yit is what? Yi is c bar a plus ca plus c bar a dagger. So expected value of dyi will give you a c times ut plus c bar times u bar t into dt plus, okay, minus, then you have expected value of this quantity jt of c bar l plus cl dagger given eta ot, that will give you pi t of c bar l plus cl dagger into dt. So you will get this sort of a value for dyot, right. So so you will get, you can substitute for, so you will put the value of expected value of dyot given eta ot into this multiplied by gtx here. So you will get this into c into ut plus c bar into ut bar minus pi t of c bar l plus cl dagger into dt, that dt I have cancelled out. So this whole thing is equal to 0. So I will get a linear algebraic equation for ftx and gtx in terms of pi t at this evaluated at theta 0x, pi t at theta 1x and pi t at c bar l plus cl dagger. Likewise, if you look at the other equation, expected value of djtx minus d pi tx multiplied by dct plus expected value of jtx minus d pi tx, jtx minus pi tx into dct. So, if you put this as 0, what do you get? You get expected value of d, you can write this, and you put fk as, you remember that in the case when there is no conservation noise, then you can write it as simply this ct multiplied by dy ot. So, if I substitute for dct into this equation, I get jtx, jt theta 0x. Okay, you are taking a product of two differentials. So, again you should take only the dA term here and the dA dagger term in dct. So, if you take the dA term in the first bracket here, you get jt of theta 1x into dA minus d pi t is gtx into dy ot. So, dy ot, here you get this into dct, dct is ft ct dy ot. So, I can keep only the dy ot term because I am going to put ft as 1 finally, and since you are multiplying it by an arbitrary ct, you can take a conditional expectation given eta ot here, right. So, this term will evaluate after taking conditional expectations, after using the fact that ct is an arbitrary element of eta ot, is an arbitrary element of eta ot, the output sigma field. So, you get this, plus here you will get plus jtx, expected value of jtx minus pi tx into dct, again you will get a dy ot here, and you are putting ft as 1 and you are taking the conditional expectation here. So, you are using the fact that ct is an arbitrary element. So, you see what happens is, if expected value of any variable times ct is 0 for all ct in eta ot, then it implies that if this is 0 for all ct in eta ot, then it implies that expected value of xi given eta ot is 0. I am just using this fact. So, now you use the formula for dy ot to evaluate this. First, when you evaluate expected value of jtx, this term, the first term will give you pi t of theta 1x into u dt into ut dt minus gtx times dy ot, but dy ot is what? Dy ot is dy it minus jt c bar l plus c l dagger dt. So, expected value of dy ot given eta ot, what is that? It is simply equal to that you will substitute here, right? And what is that equal to? Dyit is c, what is yi is ca plus c bar a dagger. So, dyit expected value will give you cu plus c bar u bar. So, it will give you cu plus c bar u bar, that is the first term, minus expected value of jt c bar l plus c l bar, there it will give you pi t of it's a small error I have made here. You see, when you evaluate j of theta 1x dA into dy ot, right, when you evaluate jt of theta 1x into dy ot, you take dA into dyo. dA into dyo will get a contribution when okay, how do you evaluate it? How do you evaluate expected value of jt of theta 1x dA multiplied by dy ot given eta ot? How do you evaluate this? You just substitute expected value of jt of theta 1x, here dy ot, the only contribution can come when you get a dA dagger from here, right, and you already seen that dyo, okay, dyot is nothing but c into dat plus c bar into dat dagger minus jt of c bar l plus c l dagger into dt. So, the only non-contribution, zero contribution can come when you take a dA dagger coming from this. So, this will be c dA into c bar dA dagger into dt, okay, this thing given eta ot, which is equal to c bar into pi t of theta 0x dt. So, you can evaluate that term in this way. Likewise, when you have a term like expected value of djtx, you had a term like this multiplied by dct. You had a term like this to evaluate. So, you will get a term like you have a dA. So, this is djtx multiplied by dct is ft yt. So, dct is ft ct dyot. So, this is 0 for all ct, this along with the other terms evaluates to 0 for all t. So, this gets replaced by expected value of djtx when you put ft as 1 into dyot given eta ot. And obviously, that will contribute only when you have an a here and an a dagger, dA here and a dA dagger term here, which we have already evaluated. But you will also have terms like expected value of jtx into dct given eta ot in the second equation. So, to evaluate that, you must be, it is more tricky. For example, to evaluate jtx into dct, this will be expected value of jtx times ft ct into dyot. Get this? And when you use the fact that ct is arbitrary, it gets replaced by a conditional expectation of the form jtx times dyot but given eta ot. You get this? So, dyot you substitute. So, you get jtx multiplied by d c dA dyi, which is c dA plus c bar dA dagger minus jt of c bar l plus c l dagger dt given eta o. So, when you calculate this, what do you get? The first term will give you c times pi tx into ut into dt. The second term will give you plus c bar times pi tx into u bar t into dt. The third term will give you see jtx into jty is jtxy. You take here x, here you take j bar cl plus cl bar. So, that will give you minus, after taking a conditional expectation, it will give you pi t x into c bar l plus cl dagger. It will give you this sort of a term into dt, and the sum of these terms is 0. Not sum of these terms, these plus the other terms in the original expression, that is 0. So, that will give you, this will give you an expression in terms of the pi t x into pi t of y, where y varies, pi t of z where z varies over system observables. So, in this way I am able to make all the calculations. I get two linear equations for ftx and gtx and gt. I get two linear equations. If I solve, I get the Kushner, I get the Bilyavkin filter. In the special case when there is no Poisson noise either in the Hudson-Parthasarathi equation or in the measurement model. So, the idea is very simple. The idea that we are, by perturbing an atom, by perturbing a system with a non-demolition noise and make input non-demolition noise and measuring the output non-demolition noise, I am able to make out what is the state, estimate the state of the system. So, finally, in the special case when the bath is in the 0 coherent state, the Bilyavkin filter simplifies drastically to something like d pi tx is equal to, if you substitute for ft and all that, it will give you pi t of theta 0 x dt plus pi t of xm dagger plus mx minus pi t of m plus m dagger into pi t of x multiplied by dyot minus pi t of m plus m dagger x, pi t of m dagger dt. So, you will get a Bilyavkin filter equation in this form. So, given it is a recursive, it is a real time algorithm in the sense that when I take an extra measurement, output measurement dA by OT, I can improve on the estimate of the state at time t. Remember that pi tx is nothing but the conditional expectation of the state of the system at time t given the measurement algebra up to time t. Now, where m is some system observable, it is expressed in terms of C and L and L dagger, C, L and L dagger, C bar, L and L dagger. I am not interested in what exactly the specific form. What I want to do now is something more delicate. I want to first I want to compare this with the Kushner-Kalyanpur filter in terms of by showing that this gives rise to extra terms which are expressed as power series in the Planck's constant. So, to do that, first I must transform, this is the Belyaevkin filter in observable form, you must get Belyaevkin filter in the state form. This is a stochastic Heisenberg equation. It is a stochastic Heisenberg equation because everything commutes here, and it is a generalization of the Heisenberg equation in the sense that if there were no noise, then it would reduce to simply dx by dt is equal to I h comma x, but here there are noise terms also. So, let us see first how do you get this into state form, and that is fairly straightforward. You have to write, when you look at pi tx can be written as the conditional expectation of the state at time t given measurements up to time t. So, this can be written as trace of rho Belyaevkin t into x, right. This is the expected value of x given in the filtered state, because this is the expected value of x given the measurement algebra up to time t. So, you expect that this must be expressible in this form, when now rho bt is a strange sort of an object. It is a state of the, it is the estimated state or estimated density matrix of the system given non-demolition measurement. So, this should be viewed as a system space matrix. It should be viewed as a system, that is, it acts in H, but its elements are functions of the output non-demolition noise up to time t. So, they all commute with each other. So, this is called the Belyaevkin filtered state. So, if you substitute for d pi tx, what do you get? You get trace of d rho btx, d rho btx. This is what is d pi tx, right, and this is equal to pi t acting on theta 0 0 x. What is pi t acting on theta 0 0 x? It is trace of rho bt multiplied by theta 0 x into dt. This can also be written as trace of theta 0 star acting on rho bt, where theta 0 is the star is the dual of theta 0 into x into dt, right, this plus other terms. So, if you write down the Belyaevkin filter equation in this form and use the fact that x is an arbitrary system space observable, I end up with a filter equation for the density conditional expectation of the density matrix given the non-demolition output measurements up to time t. So, what does it look like? You get terms like, what about a term like, you have a term like pi t of xm dagger plus mx. What will this be? This will be nothing but trace of the Belyaevkin filter state into xm dagger plus mx, this sort of a thing, which can be written as trace of m dagger rho bt plus rho bt into m multiplied by x. So, like that I get all the changes, and likewise you have a term like pi t of m plus m dagger into pi tx in the Belyaevkin filter equation for the state. This can be written as trace of rho bt multiplied by m plus m dagger into trace of rho btx. So, if I equate coefficients, of x on both the sides, I get this equation rho bt is equal to theta 0 star acting on rho bt dt, rho bt plus m dagger rho bt plus rho btm minus trace of rho bt into m plus m dagger multiplied by dyot minus trace of rho bt into m plus m dagger dt. So, this is called the Belyaevkin filter equation in state form. So, we want to make a comparison with the Kushner-Kalyanpur filter. What is theta 0 star? I write theta 0 star as simply some theta, right. So, theta 0 star is nothing but theta acting on rho b will be of the form minus I h comma rho b minus half in the special case of when there is no Poisson noise. So, L dagger rho b plus rho b L dagger minus 2 L dagger rho b L. So, this sort of a expression I will get for the dual of theta 0, namely theta 0 star. Now, let us make a comparison with the classical Kushner-Kalyanpur filter. What is the classical Kushner-Kalyanpur filter? You can also derive that from the orthogonality principle. Kushner-Kalyanpur filter is derived for the state model dxt equal to fxt t dt plus dxt t dbt, where bt is classical Brownian motion and this is a stochastic differential equation, or more generally xt can be any Markov process, and the measurement model is ht xt dt plus dvt, where dvt is a Brownian motion or some with some variance covariance, right. You can write dvt as dvt, you can write it as some rt times dbt d epsilon t, where epsilon t is standard Brownian motion and rt is a covariance matrix. So, in this case you define the capital ZT to be equal to the sigma algebra of the measurements up to time t, and you consider the conditional density of the state at time t given the measurements up to time t, and you derive a stochastic partial differential equation for this. So, it will also be of the same form. You can derive it in various ways, again using the reference probability approach you can derive it. For example, you can consider expected value of a function of the observable of the state given measurement algebra up to time t. Given the measurements up to time t, I call it as pi t phi, and I assume that d pi t phi in the same way, d pi t phi is equal to some f t phi dt plus g t phi of dz t. And if I can write and use the same reference probability approach to get these functions f t phi and g t phi, which will now be functions of the measurement process up to time t. So, you can write the basic equations as phi of xt minus pi t phi multiplied by Ct is 0. So, Ct equal to 0, where Ct is a function of Zt up to time t, and take the d of this and derive it in the same way, and finally substitute use the fact that pi t phi can be written as integral phi of xt into p of xt given zt dxt integrated over all the states, over the entire state. So, to get the stochastic partial differential equation for p xt given zt, that is one way of deriving it. The other way is to directly use the fact that the conditional density at time t plus dt can be written as p xt plus dt, the joint density of xt plus dt, then zt and dzt, the increment in the observation, divided by p zt plus dt, p zt dzt, where z small z is the measurement at time t, whereas capital Z T is the measurements up to time t, the entire cumulative set of measurements up to time t, and you can write this as p xt plus dt by using the Markovian property given xt into p xt given you can write this as p of dzt given xt into p xt plus dt given xt into p xt given zt integral over dxt divided by integral of the numerator over all dxt plus dt, and using the fact and substitute for pxt plus dt given xt the Markovian transition probability kernel, infinitesimal generator of the transition probability, infinitesimal generator of the Markov process xt. I can substitute here, and for dzt given xt I use the fact that dzt is equal to ht xt dt plus dvt, where dvt is Brownian motion. So, I can easily write down the conditional probability of pz dzt given xt as express c a constant times c e power minus dzt minus ht transpose RT inverse dzt minus ht, and substitute it, make all the cancellations, and finally derive the Kushner-Kalyanpur filter equation in the form dptx given zt. Ptx means this is the conditional density, conditional probability density of xt given the measurements up to time t. It is the conditional probability, it is ptx is equal to the forward Kolmogorov operator LT of the Markov process, or the generator of the Markov process, the dual of the generator of the Markov process LT star acting on Pt x given zt. LT is the generator of the Markov process into dt plus plus what? First you note in the observable form that pi t phi will have the form pi t of LT phi, pi t of LT phi dt plus pi t of phi h t minus pi t of phi into pi t of ht, this into dzt minus pi t of ht dt, where ht means, by ht I mean h of t comma x, this function. Okay. So, in observable form using the reference probability approach I get this, and then I take the dual and switch over to densities. You see, in the case of classical probability theory, the dual is simply defined by the inner product, right. So, you do not have to worry. In the if you have a probability density rho in quantum theory, and you have an operator L acting on x, then this could be written as trace of L star rho into x, that is the dual. That is the dual of L, that defines the dual of L. In the case of classical probability, you will have a probability density function p times an operator acting on an observable phi, and then you take dx. So, this will be equal to simply the adjoint of the operator p L acting on p into phi into dx, right. Traces are replaced by multiplication over by integration over the state variable. So, here you have this sort of a term. These two terms will give you what? Pi t phi ht can be written as integral conditional density into phi into ht dx. So, it will be replaced by, if you remove the phi, if you take the dual, this will be simply ht into p, right. So, this will be simply plus it will be equal to integral p pt x given zt So, that will not be an integral, right. It will be pt of x given zt multiplied by h of tx minus minus pi t of phi. So, here you will have pi t of ht, which is integral of htx pt x given zt dt multiplied by pi t phi. So, there you will have pt of x given zt, you get this sort of a term. So, you will get this multiplied by dzt minus integral of htx ptx given zt dx into dt. So, this is called the Kushner-Kalyanpur equation, where LT is the generator of the Markov process and LT star is its dual. So, let us make a comparison. To make any comparison between classical and quantum mechanics, you see, in quantum mechanics two observables do not commute. When they do not commute, you cannot talk of a joint density, but Wigner introduced what is called today the Wigner-Ville distribution or Wigner-Ville density, which says that you can approximate when two observables have uncertainty, you cannot measure them simultaneously like position and momentum, but what happens is that uncertainty is of the order of Planck's constant. So you can divide the whole phase space into boxes of length Planck's constant, and and within each box you get an average density. So it is introduced, for example, if rho is the density of a system and you look at its representation in position representation, you call it as rho q dash. So this is a complex valued function of q and q dash, there are two variables. So obviously to calculate trace of rho x, similarly for observables you can do the same thing, qx q dash in the position representation, this is x q q dash, this is a matrix, continuous matrix. So trace of rho x becomes what? Trace of rho x becomes integral rho q q dash into x q dash q dq dq dash, right. You can write this in this form. So you introduce boxes, you have delta p into delta q is of the order of Planck's constant. So you introduce a Fourier transform taking this uncertainty to account. So instead of rho q q dash describing the density like this, you can write it as you can consider rho of q plus q by 2 and q minus q by 2 into e power minus I pq by h cross into dq, or plus, let us put a plus side, and you take into a constant and you call this as the joint density of q and p, position and momentum. Now this is a complex valued function of q and p. In general it could be negative, it could be complex, it could be anything, but it has got certain nice properties. For example, if you integrate wqp over all p, if you integrate this over all p, then what do you get? You get, if you integrate, use the fact that integral e power I pq by h cross dp is nothing but 2 pi delta, integral of this over p is delta q by h cross, which is equal to 2 pi h into delta q. So if you integrate this over p, you will get what? You will get c into 2 pi h multiplied by rho at q plus q by 2, q minus q by 2 d small q. So that will give you rho of q, which is the density of q, right, provided you take c as 1 by 2 pi h. So if you integrate this over all p, I get the density of q, probability density of q. Likewise, if you integrate wqp over all p, what do you get? If you integrate this over all p, over all q, not over all p, if I integrate this over all q, what do I get? Just try to compute and see. If you integrate this over all q, you take rho of q plus q by 2, q minus q by 2 into e power I p q by h dq, and then you integrate over all q, what do you get? You can write this as rho of q1 comma q2 e power I p by h cross, then this q will become q1 minus q2, and I am writing q plus q by 2 as q1 and q minus q by 2 as q2. So this will become dq1 dq2, and this is nothing but the Fourier transform of rho q1 q2, bivariate Fourier transform of rho q1 q2 with respect to the first variable and then with respect to the second variable evaluated at pp. So you note that the momentum wave function, what is the momentum space expression of the density matrix? It is equal to e power I p1 q1 minus p2 q2 by h dq1 dq2 is equal to the Fourier transform of rho with respect to, this is a momentum space wave function. So this is equal to rho cap of pp, which is nothing but the density of the momentum p, probability density of the momentum p. So if you integrate the Wigner-Ville distribution, if you integrate wqp with respect to q, you get the density matrix of P, you get the probability density of P. You can measure the density alone, you can give meaning, but you cannot give meaning to the joint density of P and Q. You can give sense to the marginal densities of P and Q, and that is this. And if you integrate QP dP, you will get WQQ, which is the density W. You will get rho of QQ, which is the density of Q alone. Remember, how do you define positions momentum space wave function? Momentum space probability density is nothing but P with rho with P. So suppose you want rho cap P, say you want rho P1 P2, you want to specify the density matrix in the momentum domain, then this is P1 rho P2, which could also be written as P1 Q1 dQ1 rho Q1 rho Q2 dQ2 multiplied by Q2 P2 integral dQ1 dQ2. You could also write here, and you note that P1 Q1, this transition function is given by a constant times e power so e power I P1 e power minus I P1 Q1 by H. You can derive this from the fact that P1 is of the form dou by dou Q1 with a negative sign minus I H cross dou by dou Q1, and use the fact that minus I dou by dou Q1 acting on Q1 P1 is equal to P1 times Q1 P1. It is an eigenstate of the momentum operator, this density, which shows that Q1 P1 is nothing but e power I P1 Q1 by H cross into a constant, or equally P1 Q1 is the conjugate of this, which is given by this. So you can give meaning to the marginal density. That means if you look at the Wigner-Ville distribution, it has got nice properties. Its integral over all position is simply the momentum space probability density, probability density of the momentum, and the integral of WQP over all P is the probability density of the position, no hat, rho Q1 rho QQ. So now we try to now formulate the Belyavkin filter using, you express the density in terms of, instead of, you replace the density matrix by the Wigner-Ville distribution, and you make comparisons between the differential equation satisfied by WQP. It is an ordinary complex valued function of two variables Q and P. You make a comparison between the differential equation satisfied by W and that satisfied by the joint density of position and momentum for the simple case when you have a particle moving in a potential with Brownian motion, Brownian noise and so on. For example, if you take a simple particle in classical probability theory, it has mass 1, so its governing stochastic differential equation will be given by this, right, dPt is equal to minus of the potential, derivative of the potential at qt dt minus, you can put a gamma, you can put a damping constant gamma pt dt, and you can put a Brownian motion sigma of sigma dBt, where this is a Brownian motion. In this case, you can ask what is the equation satisfied by the joint density of Pt and Qt, P QP. What is the equation satisfied by this? You know from Fokker-Planck equation theory, basic theory in stochastic differential equations, that this will satisfy a forward Kolmogorov equation, namely dou Pt Qp is equal to minus P dou Pt Qp by dou Q plus U dash of Q dou Pt by dou P plus gamma times dou by dou P of P into Pt plus sigma square by 2 dou square P by dou T square, Pt by dou P square. So except for this, if this damping is there, it is fine, it also is fine, but there is an extra fluctuation term. So we want to derive such a Fokker-Planck equation in the quantum case also for the Wigner distribution WQP as a function of time t from the basic equations of quantum mechanics. So to do that, first you look at what is the Hamiltonian for such a Langevin particle. It is p square by 2, I am taking m as 1 plus u of q. This is the quantum mechanical Hamiltonian H, and the equation satisfied by the density is what? The equation, Schrodinger's equation for the density is dou rho t by dou t is equal to h comma rho t, h comma rho t, where p is equal to minus I h cross dou by dou q. So now if you when you do not have noise, this is the simple model for what takes place here. When you have noise, then you have an additional term which you can write as theta of rho, where theta is represent the Lindblad noise, which can be written as minus half LL dagger rho plus rho LL dagger minus 2 L dagger rho L. So let us look at what happens in the Wigner distribution domain. How does this equation translate to in the Wigner distribution domain? This can be viewed upon as an equation for the matrix rho q q dash, right, where this is equal to q rho t q dash. So to go over to the Wigner distribution domain, what do you have to do? You have to express things like h comma x, h comma rho, etc. in terms of the Wigner distribution. So let us see how to do it. For example, if you take an observable, say you take a Hamiltonian H, say you look at WQP, how you define WQP? The Wigner distribution is a constant times rho of q plus q by 2, q minus q by 2, e power I pq by h cross into dq into a constant. So if you look at WQP, if you look at you want to compute the expected value, say you look at trace of rho x, you want to compute this can be written as rho q q dash x q dash q dq dq dash, right? You can write it in this form. Now you substitute for rho q q dash the expression, the inverse of this, right. So if you from this equation, it will follow that the inverse is given by rho q q dash is equal to, you first take the inverse Fourier transform. So this will be WQP QP e power minus I p by h, and instead of small q you put q minus q dash, okay, integral dq dq dash apart from a constant. So integral dq integral dp it should be integral dp into a constant. So you can express the quantum mechanical density matrix in the position domain in terms of the Wigner distribution, which is a complex valued function of two variables q and p, two real variables q and p. So if you substitute this into rho q q dash, and likewise for observables you do the same thing. So you have x of q comma q dash, I define it to be integral x1 of qp I define it to be x1 of no, let us just, okay, I define x1 of qp to be equal to integral x of q plus q by 2 q minus q by 2 e power I pq by h cross dq. I define this so that the inverse becomes f of x of q comma q dash, which is a quantum mechanical quantity as a function of q and q dash. This is equal to constant times x1 of q plus q dash by 2 p e power minus I p e power minus I p q minus q dash dp into a constant. Likewise rho of q q dash equals integral rho of rho 1 is also w, right. So rho 1 of qp, I define this to be w of qp. So rho 1 of qp, which is a classical quantity, q plus q dash by 2 comma p e power minus I p divided by h cross, p into q minus q dash by h cross dp. So now I compute the expectation. So to compute the expectation, I must put trace of rho q q dash x of q dash q dq dq dash. Okay, so this will be equal to simply rho 1 of q plus q dash by 2 q plus q dash by 2 p, then e power minus I p by h cross q minus q dash into x. So, x1 of q plus q dash by 2 comma p dash e power minus I p dash by h cross into so q dash and q I am taking, right. So, here it is q minus, here you have q dash minus q, then dp dash and then dq dash. So, you compute the expectation. So, if you make all the simplifications here, for example, if you write q plus q dash as a new variable, and if you write q plus q dash by 2 as a new variable I introduce, and q minus q dash as another variable. So, I say q plus q dash by 2 equals q1 and q minus q dash equal to by 2 equal to q2. Suppose I define it in this way, then this integral becomes rho 1 of q1 p into x1 of q1 p dash into e power minus I p by h cross q minus q dash is 2 q2. So, 2 q2, then here you have e power minus I p dash by h cross q dash minus q is minus 2 q2. So, 2 q2 and then here you have an integral. So, you have an integral with respect to dq and dq dash. So, dq dash integral becomes dq2 dq1. If you integrate over dq2, you get a delta function of p minus p dash. So, this will become, so this whole integral will become simply integral rho 1 of q1 p into x1 of q1 p dq1 dp1. That means that you can compute the expectations. This is trace of rho x. This is nothing but trace of rho x. You can compute the quantum mechanical expectation as though it were using a classical probabilistic expression of an integral integral of the observable of the random variable multiplied by its density, provided you assume that densities and random variables can take complex values. So, you can make an analogy between classical probability and quantum probability theory by replacing probability densities by complex valued functions of q and p, right. So, what about things like, suppose you look at a Heisenberg equation of the form dx by dt is equal to I times h comma x. I want to, and in classical mechanics you know that observables satisfy Poisson bracket relation dynamics, that is the rate of change. If x were viewed as a function of q and p, then this will satisfy dou x1 by dou q into q dot plus dou x1 by dou p into p dot, where q dot is by Hamiltonian mechanics dou h by dou p and p dot is minus dou h by dou q. So, this will be nothing but the Poisson bracket between x1 and h, right. So, at qp. So, curl denotes Poisson bracket, square bracket denotes Lie bracket. So, can I make an analogy? Can I derive something like the Poisson bracket relation for x1 into x1 and for x1 in terms of h1 by passing over to Wigner-Ville distribution ideas? So, the answer is yes, and we can do it. So, for example, if you have say d by dt of x equals I times h comma x, what happens if you take the Wigner distribution on both sides? This will become d by dt of x1 of qp, and this is equal to I times h comma x 1 at qp. So, I have to evaluate this using some Poisson bracket ideas. So, let us see how we can do it. So, you have h, let us say first hx, I take two observables, multiply them in quantum mechanics, compute the Wigner distribution part by putting a script 1 below. This is the Wigner distribution. So, this is hp hx 1 of qp. This can be written as h of, so this is nothing but hx of, in the position representation it becomes q plus q by 2, q minus q by 2, e to the power I p q by h cross dq, like this. So, you can write this as hx1 at qp is nothing but integral h of so this is nothing but hx of q plus q by 2 q minus q by 2 e to the power I p q by h cross dq, which can be written as ordinary matrix multiplication. So, h of q plus q by 2 comma q dash into x of q dash comma q minus q by 2 dq dash into e power I into e power I pq by h cross dq dash. This is an ordinary matrix multiplication of the matrix representation using matrix representations of observables. So, now what can I do further? I want to express this in terms of h1 and x1. So, I substitute for this. So, I substitute the inverse formula for h1. So, h1 of this becomes q plus q dash by 2, this becomes q plus q dash by 2 plus q by 4. H of q q dash, what is h of q q dash? H of q q dash by the inverse formula is a constant times h1 of q plus q dash by 2, then p into e power minus I p by h cross q minus q dash dp, that is the inverse formula. So, substitute that here, here you take this plus this by 2 and then comma I put a p here, and I put similarly x of x1 of q dash plus q by 2 minus q by 4 comma p dash, and then I put a factor of e power minus I p by h cross into the difference of these two, which means q minus q dash plus q by 2 into e power minus I p dash, the difference of these two, which is nothing but q dash minus q plus q by 2. So, q dash minus q plus q by 2, get this, and then here I put a e power I p q by h cross, then dq dq dash dp dp dash, I put all these terms together. So, and I evaluate them. So, the idea here is to substitute q plus q dash by 2 plus q by 4, sorry q plus q, I substitute q plus q dash by 2 plus q by 4, I write this as q plus xi times some Planck's constant, and I write q plus q dash by 2 minus q by 4 as some eta times a Planck's constant, and expand in powers of h cross, expand both sides in powers of h cross. So, wherever you have such a thing, this will become something like, so you have h of something like h1 of q plus q dash by 2 plus let us say q by 4 here comma p, I have something here. So, this will become h1 of q plus xi h comma p, which can be written as h1 of q comma p plus dou h1 qp by dou q into xi h plus half dou square h1 qp by dou q square into xi square h square, and so on. So, if I substitute all that and use the fact that make use of relations like e power I xi, just 1 minute. So, I make use of relations like e power I xi p minus p dash, I power I xi p minus p dash d xi, this is equal to 2 pi delta xi minus xi dash delta p minus p dash. If I make all these substitutions, then you will get a remarkable fact that if you consider for example h into x 1 at qp, h into x hx 1 at qp, that will be simply that will be simply a thing like that will be H1 at QP, H1 at QP, X1 at QP, X1 at QP, X1 at QP minus IH by 2 times the Poisson bracket between H1 and X1 at QP plus order H square. You will get this sort of a relationship. It means that where your order H square terms, the order H square term, this order H square term is something like 1 H square by 4 times dou square H1 QP by dou Q dou P into dou square X1 QP, okay, by dou P square minus 1 by 4. So, dou square H1 QP by dou Q square into dou square X1 QP by dou P square minus a term of the form dou square H1 QP by dou P square into dou square X1 QP by dou Q square. So, you get order H square terms. What is important here is that here the first term is simply a product of classical functions of Q and P, which are complex valued functions. The second term is a Poisson bracket, right. So, if you look at, for example, in particular H comma X and then 1 at QP, the classical form of this Poisson bracket, which is nothing but Hx1 minus Xh1 at QP, then the first terms will cancel out. You will get simply IH times the Poisson bracket between H1 and X1 at QP plus order H square terms, which you can calculate in the way I just indicated. So, what will happen is that, for example, if you look at a Heisenberg equation of the form dx by dt is equal to I times H comma X, it will translate to dx1 by dt as a function of t, q and p for a complex valued function of q and p. This is nothing but I times the Poisson bracket between H1 of t comma qp and X1 of t comma qp plus order H square terms. This will be this I won't come, this will be a Poisson bracket plus order H terms, which can be calculated using the double derivatives of H1 and X1 with respect to q and p. So, the quantum equations give you an approximate version, yield an approximate version of the classical Poisson bracket relations if you make these identifications. Now, suppose you take, let us say you take an equation of the form, dou rho by dou t, t is equal to minus I H comma rho t for the quantum mechanical equation for the density matrix or density operator minus half times something like the Lindblad operator. So, LL dagger into rho plus rho LL dagger minus 2 L dagger rho L. Suppose you take this sort of an equation and you do the same transformation, let us say, so these terms will give you the usual Poisson bracket. You try to calculate the equation satisfied by rho 1 of QQ, rho 1 of QP as a function of time t. So, you will get dou by dou t of this and here you will get a Poisson bracket, which is the Liouville equation for the density minus I times the Poisson bracket between H1 and rho 1 plus order H square terms, and these terms will give you second order derivatives. This will give you second order derivatives with respect to rho 1, which will correspond to Fokker-Planck terms, Fokker-Planck correction terms. For example, suppose I take L as simply multiplication by Q, then what is LL dagger rho? If you write it in the position representation, Q dash, this is nothing but UQ square multiplied by rho Q dash in the position representation. Similarly, if I write rho LL dagger Q dash, this will be simply UQ dash square, U dash square rho Q dash. If you write L dagger rho Q, L dagger rho L at Q dash minus 2, that will give you minus 2 uq into uq dash into rho of qq dash. So, this whole Lindblad operator acting on this, if you look at the Lindblad operator acting on rho in the qq dash representation, this is nothing but uq minus uq dash square multiplied by rho qq dash. So, now you take the Wigner-Ville distribution on both sides, transform on both sides, apply the Wigner-Ville transform on both sides. What do you get? You get that this acting on rho, and then you take 1 at qp. That is the classical, the Wigner-Ville distribution of theta rho. That is nothing but uq plus uq plus q dash by 2, uq minus uq dash, right. So, just one second, uq minus uq dash square into rho of q comma q dash. You are taking the Wigner-Ville transform of this. So, you replace q by q dash plus q by 2. So, this will become u of q plus q by 2 minus u of q minus q by 2 square multiplied by rho of q plus q by 2 q minus q by 2 e power I p q by h cross dq. This sort of a thing you will get. Now, you replace the variable, okay, call q as xi times h cross, right. You introduce a new variable q is equal to xi h cross, then this becomes u of q plus h xi by 2 minus u of q minus h xi by 2 square, this square multiplied by rho of so you are taking the Wigner-Ville transform on both sides. Multiplied by rho of q plus xi h by 2, then here you have q minus xi h by 2 e power I p xi d xi into a constant. So, if you expand this, so if you are looking at theta rho 1 at qp, you want to express this in terms of the Wigner-Ville distribution of rho 1. So, if you write down the expression for rho q in terms of its Wigner-Ville distribution, what do you get? You get, if you write down this expression, this can be written as u of q plus h xi by 2 minus u of q minus h xi by 2 square multiplied by this can be written as rho 1 of q plus p by 2. So, that will be this plus this by 2 will give you q comma p into e power I p xi into e power I p xi into e power so rho of q e power I p xi d xi. So, in terms of p it will become e power I p the difference is will give you xi e power I p 2 xi. So, it will be I p 2 xi, it will give you this sort of a thing, and q plus q dash by 2 into the difference of these two, which is xi. So, into dp xi, right. So, it will give you and you are integrating over xi, right. You are replacing q, what do you replace? You replace rho of q q dash, you replace rho of q q dash by rho 1 of rho 1 is the Wigner-Ville distribution, q plus q dash by 2 comma p e power minus I p q minus q dash. So, q minus q dash by h cross, and then you put a dp here, right. So, you write this in this form. So, rho q of p dash I should put. So, p dash e power, that one be a 2 here, be a factor of e power minus I p the difference minus I p dash into xi into e power I p xi d xi. So, if you integrate over xi, you will get a you cannot just integrate directly, you have to first expand this, right. So, what will happen is that if you expand this term, what do you get? You will get uq, the 0th order term gives you nothing. If you expand it in powers of Planck's constant, this gives you u dash of q into h xi plus u double dash of q into xi square. That will not give anything. So you forget about this term, right, plus order h square. You can calculate that h square h cube terms by expanding it in further, and this multiplied by rho q p dash multiplied by e power I p minus p dash into xi d xi. Now if you look at, for example, xi into e power I p minus p dash, that gives you a derivative of the delta function. So you will get a term like u dash of q times the derivative delta dash at p minus p dash, and you are multiplying by rho q p dash and taking this. So this will be nothing but rho 1. So this will be rho 1 q p by dou p, which is precisely what you get in the Fokker-Planck equation, the same term that you get in the classical Fokker-Planck equation. So you will get that. If you look at the other terms, for example, order h square h power n, suppose you look at order xi power n terms, in that xi power n term will give you a derivative, of the delta function, nth order derivative of the delta function evaluated at p minus p dash. So that will give you an nth order derivative of rho 1 with respect to p. So you will get higher order correction terms in powers of Planck's constant. In other words, you are able to reproduce the equation. If you look at the equation, dou rho by dou t is equal to I times h comma rho plus theta rho, the Lindblad equation. In the classical sense, it becomes, when you take the Wigner-Wille distribution, this becomes rho 1 of q p t q p is equal to the Poisson bracket between h1 q p and rho 1 t q p. Rho 1 is same as the Wigner-Wille distribution, the same notation I am using just for consistency. This plus order h term. So one term which you will get is of course something like u dash of q, as I just saw, u dash of q times dou rho 1 by dou p, which came in the Fokker-Planck equation. But you also have a term like sigma square dou square rho 1 by dou p square. You need this sort of a term to get the noise. That will come from the second order term. That is, if you look at the uq plus xi h by 2 minus u q minus xi h by 2 square, you had something like this, and then you had rho 1 of q p dash e power I p minus p dash xi. You had this sort of a term, right, d xi. If you look at higher order expansions, if you look at higher order expansions in powers of Planck's constant, you will get those terms also, right. You had you can just check this, right. You can just see, you have say LL dagger, you have this theta of rho was replaced by what? It was replaced by uq minus uq dash square times rho of q dash, and you take the Wigner-Wille distribution of this, it becomes q plus q by 2 minus u of q minus q by 2 square into rho 1 of rho of q plus q by 2 into rho, so that you have rho of q plus q by 2 and q minus q by 2. So that become rho 1 of the sum by 2, which is q, and rho 1 of the sum by 2, and then p dash, and then here you have e power minus I p dash times q by h cross. You have this sort of a thing, and you are taking the Wigner-Wille transform of this, right. So q plus q dash by 2, q minus q dash, and e power I p into q minus q dash, sorry, e power I p into so q plus q by 2, q minus q by 2, e power this, so rho 1 of q p q dash into the difference of these two. So, the difference was q minus q dash 1 of q. See, when you write rho of q dash, when you take rho of q dash, you could write this as integral rho 1 of q plus q dash by 2 comma p e power minus I p into q minus q dash dp. So, here you are using p dash. So, you are using the p dash variable here. So, e power I p dash times, here you are taking q dash, right. So, it should be simply q plus q dash by 2 gets replaced by just try to understand what we are saying here. Okay, this will be, if you take the Wigner-Wille distribution of this is you replace q by q plus q dash by 2, rho q dash, and I am taking the Wigner-Wille distribution of this side. So, this is q plus q by 2 minus u of q minus q by 2 square multiplied by rho of q plus q by 2, rho of q by 2 q minus q by 2 e to the power I p q by h cross dq, and then you replace this by, you replace your rho by this expression. So, it will become rho 1 of q plus q dash by 2, which is rho 1 of q comma p dash into e power minus I p dash times q minus q dash. The difference of these two is q, and here you have e power I p q by 2. Yeah, now it is okay, by h cross dq, and then you integrate with respect to p dash dp dash. So, you can get second order terms. How can you get second order terms in this equation? So, if you expand this in powers of q, if you expand this in, if you replace q by h by xi and expand it in powers of xi, you will get second, third order terms also into the picture. The second order term may not come in this way, but it will come if you take two different functions. For example, if you take your L as say some function of q and p, then or you take some function of q and, or some function of rather q and dou by dou q, minus I dou by dou q, and then you go to the Wigner domain, then you will get the higher order terms in Planck's, in powers of Planck's constant. Okay, so that is the brief idea. Now, if you take the Belyavkin filter, what happens is you have an equation of the form d rho bt is equal to say theta 0 star acting on rho bt, theta b the 0 star acting on rho bt minus rho m1 or rho m plus m dagger rho bm plus m dagger rho b minus trace of rho b into m plus m dagger multiplied by rho b into dy minus trace of rho b into m plus m dagger dt. You have this sort of a thing. So, if you do the same replacements here, what do you get? You get for theta for you get, of course, this will become the forward equation, forward Fokker-Planck equation. Theta 0 you can expand it, like you will, if you represent rho b by the Wigner-Wille density, that means you write rho b t as rho b t q dash into this is the density matrix. So, rho b of t q plus q by 2 q minus q by 2 multiplied by e power minus I p q by h cross dq. If you define this to be equal to rho b1 of t comma q comma p, and you take you apply this transform to both the sides, then you will get d of rho b1 of tqp is equal to, now theta 0 star is the Lindblad operator acting on rho bt, and we saw that could be replaced by a Fokker-Planck operator acting on the density of rho bt, joint density of rho bt. That means that it will be the forward operator which I call L dagger acting on rho b tpq, rho b1 tpq plus powers plus order h cross, which you can calculate by the method I just told you, plus these terms will also arrange the same thing. For example, if you have rho bt into m, this sort of a multiplication operator, that can be represented as what? Suppose you take two matrices, say rho b into m, Okay, let us call in general x into y, two observables, and you are taking q and q dash, and then you take the Wigner-Wille distribution of this. What do you get? You get xy of 1 of q of p, right, qp, that will be equal to x1 of qp, y1 of qp minus IH, as I pointed out, into the Poisson bracket between x1 and y1 at qp. Right. So, how do you do that? Simply look at xy at 1 at qp, and you write this as xy at q dash, xy of q plus q by 2, q minus q by 2 e to the power I p q by h cross dq, and you substitute for x. So, you write it as q plus q by 2 comma q dash, y of q dash comma q minus q by 2, then e power I p q by h cross dq dash dq, and you substitute for you substitute in this equation, you express x in terms of x1, y in terms of y1, and make all the manipulations which I just indicated. So, you will get x1 of qp into y1 of qp minus IH times the Poisson bracket between x1 and y1, x1 y1 at qp. So, you will get this extra Poisson bracket terms when you calculate. When you look at the term in the Belyavkin filter of the form rho b into m, and you evaluate this at TQP, you will get simply the x1. So, this is to be interpreted as rho b1, the density, the Wigner-Wille density of qp. You will get this term into m1 of qp plus the Poisson bracket minus IH cross times the Poisson bracket between rho b1 and m1 at q and p. So, this is like multiplying, taking h into rho. Like in the Kushner-Kalyanpur filter, we had a term like pi t of phi h minus pi t phi pi t h. You had this sort of a term, right, in the observable domain. So, in the state domain, in the density domain, what did it give you? It gave you a term like h of t. Here qp you will use, because q and p are the classical variables which we are describing in this dynamical system. Okay, for a particle moving in a potential subject to damping and fluctuations. So, you have ht qp multiplied by the density of qp given the measurement up to time t. So, you will get this sort of a term here, and here you will get pi t of phi, pi t of h. So, you will get pt of qp given zt multiplied by pi t of h is nothing but the expected value of h with respect to this density, that is ht qp multiplied by pt qp given zt dq dp. So, this term will contain, this is like looking at h, right. This term ht into pt qp is played by this product. This term corresponds to this product. This is the density, joint density of q and p in the Wigner-Wille density of q and p multiplied by m1 qp could be regarded as the observable being measured. And the other term which you got was trace of rho b into m plus m dagger multiplied by rho b. So, after taking the Wigner-Wille distribution transform, this will become, as we saw, this trace could be evaluated using in the Wigner-Wille domain, namely rho b t qp multiplied by m plus rho b1 of t qp multiplied by m1 plus m1 bar at qp dq dp. That is because you could evaluate into rho b1 of t qp. That is because you could evaluate the expectation. Trace of rho b into m. This could be evaluated using in the Wigner domain exactly without any approximation. Rho b1 of t qp into m1 of qp dq dp, where m1 is the Wigner-Wille transform of m and rho b1 is the Wigner-Wille transform of rho b. So, all the terms will correspond, but these terms will not give you any error, but the terms like rho b into m plus m dagger into rho b multiplied by this term will give you an error. This term will give you rho b1 into m1 plus m bar 1 rho b 1, they all commute here, plus order plus h cross times the Poisson bracket between rho b 1 and m. So rho b 1 comma m 1, you will get a Poisson bracket term with an IH. Here also you will get a Poisson bracket term between IH dagger and this. So it will be plus IH times the Poisson bracket between m1 bar and rho b 1. What is the Wigner distribution of m dagger in terms of the Wigner distribution of m? You can find that out very easily, right? If you want the Wigner distribution of m dagger, so 1 qp, you want this, then this is nothing but m1 dagger at q plus q by 2, q minus q by 2, e to the power I pq by h cross dq, which could also be written as integral m1 bar of q minus q by 2, q plus q by 2, e to the power I pq by h cross dq, which could also be written as integral change q to minus q, small q to minus small q. So this is q plus q by 2, q minus q by 2, e to the power, if you change it and then take a bar, so it will become e power I pq by h cross dq whole bar, which is nothing but the Wigner distribution of m1 at qp whole bar. So everything will correspond to in the same way. Wherever you have products of matrices, there you will get powers of Planck's constant as correction in the whole picture. So you can calculate in principle the corrections to the Kushner-Kalyanpur filter caused by non-commutativity. In the special model where we assume that you are having a particle moving in a potential subject to noise and damping, that means you have an equation of the form P dt and dpt is equal to minus u dash of qt dt minus gamma pt plus sigma dbt. In such a situation, you can easily get the analog of the Kushner-Kalyanpur filter in terms of you can get the analog of the Kushner-Kalyanpur filter by replacing by where the Lindblad operators will be expressed in terms of the functions u, gamma and sigma, right. So it is possible to do it in principle. Now before I conclude, I would just like to make a small addition to my whatever I have discussed today, namely that the Hudson-Parthasarathi quantum stochastic quantum Ito's formula can be derived simply, very simply, using simply harmonic oscillator algebra, using the harmonic oscillator algebra. So you have a sequence of annihilation operators n equals 1 to infinity and a corresponding set of creation operators n equals 1 to infinity satisfying the bosonic commutation relations an comma am dagger is delta nm and an comma am is 0. So this is called a sequence of harmonic oscillators. So suppose I introduce a separable Hilbert space with an orthonormal basis En, okay, and then I define for any u belonging to H, I can expand u as summation un En, where un is nothing but En with u, this inner product. So I define A of u to be equal to summation an un bar over n, or in other words A of u is nothing but summation, you can also write this as an, then here you have u with En summed over n. Similarly A u dagger becomes summed over n, an dagger En with u. So by using the bosonic commutation relations, immediately I deduce that Au comma Av dagger, this is equal to An comma Am dagger you take, right. So that will give you delta Nm. So this will give you simply An comma Am dagger multiplied by u with En multiplied by Em with u, summed over n and m, which is delta Nm. So this becomes summation u with En with u, En with v, sorry A comma I put v here, right, this is v, which is simply u comma v. That means I deduce that the commutation relation Au comma Av is equal to u comma vi. What about the conservation process? Okay, from this equation, suppose I replace u by u into chi 0 t. right. For example, my Hilbert space which I am choosing, it can be L2 R plus, or it can be more generally L2 R plus tensor CD, right, a d-dimensional Hilbert space. In that case, of course, you have you are choosing u to be u times chi 0 t, where chi 0 t is the indicator function of the interval 0 to t. So, if I define a of u times chi 0 t, if I call this as AT, ATU, and similarly the dagger I call it as AT dagger u, then I have the relation, this relation will imply that ATU comma AT dagger v is equal to u comma v is u comma v is can be written as integral of us comma vs ds from 0 to t, where us takes values in CD and vs also takes values in CD into identity. So, AT comma, you can more generally have ATU comma ASV dagger. Here you have t, you have ASV dagger, that will be equal to integral 0 to minimum of t and s. Here you will have us u alpha comma v alpha d alpha, from which you get by taking the difference, the differential, and using the fact a da dagger, using see what you do is, if you look, you are looking at ATU given by summation over all n an into En. So, En with u means you are putting here u with En, right, which is nothing but summed over all n an into sorry, this into, that's just a mistake I have made here. It should have been a u into chi 0 t with En. You are taking the special case when u is 1, so it becomes simply AT is equal to summation an into chi 0 t with En. Similarly, AT dagger is summed over n an dagger, then En with chi 0 t. So, from this equation it is clear immediately that dAT dagger dAT is 0. That is because if you multiply, if you look at say something like AT dagger into AS, suppose you look at this product, this is nothing but AN dagger AM times EM, En with chi 0 t multiplied by chi 0 s with EM summed over n and m. So, if you take d with respect to first, this term will give you integral En t ens ds from 0 to t, this will give integral EMS from 0 to s. So, if you take the double differential with respect to t and s, you will get a dt ds term which cannot cancel out, which will be of odd, and if you put ds is equal to dt, you will get a dt square term. So, you will conclude immediately that if you take first the differential with respect to t and then with respect to s and put s is equal to t, you will get this as 0, this will be order dt square, which you can take as 0. But if you look at the other way around, if you look at a dat dagger, what happens is something curious. Here you look at AT into AS dagger, this is nothing but summation an am dagger, then AT, here you are representing it as here it is chi 0 t with En multiplied by Em with chi 0 s summed over n and m. But you already know that An am dagger can be written as An comma am dagger plus am dagger An, and this is delta nm plus am dagger An. So, this becomes simply summation over all n, then chi 0 t with En multiplied by En with chi 0 s plus the other term which is As dagger At plus As dagger At, and this does not sum to give a non-trivial term. If you sum this, this becomes the inner product between chi 0 t and chi 0 s, which is chi of 0 and minimum of t and s. So if you take first the differential with respect to t, then with respect to s, you get a dt ds into delta function of t minus s, which can also be written as dt times the Kronecker delta of t and s, right. So when you put s as t, you get a dt term. That means if you use the fact that, it means in other words you get that at comma as dagger is the minimum of t and s, in which case you will get the dat dagger is simply equal to dt. So that is one aspect of this. The other aspect is the conservation process. In most textbooks and also in the notes of many mathematicians, the conservation operator is a bit of a problem. You have to define it through the while operator, but you can define it directly in terms of the number operator in quantum mechanics, namely an dagger am times you put en here, you put h here, you put em here, summed over n and m. Suppose I define lambda h in this way, then I get all properties of the conservation operator, where h is assumed to commute with the indicator function. For example, if the Hilbert space is L2 R plus tensor CD, then H is a D cross D matrix, constant matrix, and En is an orthonormal basis for this Hilbert space. In that case, what you get is that if you look at the expansion for AU as summation n an, then u with an, you look at this, and suppose you look at AU comma lambda h, you look at this, what do you get? You get an comma am dagger. Okay, an will not commute with an dagger, but an comma am is 0. So you will get, this is simply summation an comma an dagger, that is you are getting, look at it as ap comma an dagger am, then en with h with em, and then here you have u with ep. So this will give an ap comma an dagger into am plus an dagger into ap comma n. Only one term will contribute, namely when ap comma an dagger when p equal to n. So this will become equal to, this is a sum over p n and m. So this will give you delta pn. So it will give you am into en h with em, and then here you are putting n equal to p. So this becomes u with en. So it becomes, I can write this as summation am u with en multiplied by en with h with em, summed over n and m, which is nothing but, if you first sum over n, you get u comma h em multiplied by am summed over m, which is nothing but summation of h star u with em multiplied by am, which is a of h star u. So you get the relation that au comma lambda h is nothing but a of h star u, from which you can deduce all the commutation, all the quantum Ito's formula for the product between annihilation differentials and conservation differentials by replacing h by h chi 0 t. Okay, if h is assumed to be an operator which commutes with the indicator function. So by replacing h by h with chi 0 t, of course this is true for any, this equation is true for any operator h in this space. So in particular, if I replace h by h chi 0 t, where h is a constant d cross d matrix, and u by u into chi 0 t and chi 0 s, then I will get the other Ito's formula, namely dA d lambda is equal to dA d lambda, I will get dAtu multiplied by d lambda th. But if I call lambda of h chi 0 t, if I call this as lambda th, then this will be this is equal to simply dat at h star u, right. Likewise, d lambda th into dat u dagger will be dat dagger at h star u. So you will get all the remaining quantum Ito's formula very simply. You do not have to go to the while operator. You can directly introduce the conservation operator through the relation lambda of h is equal to summation an dagger am times en with h with em. summed over n and m and proceed. So, this has a natural interpretation in the sense that quadratic forms in ANs represent the number of particles. So, lambda h has all properties of a quantum Poisson random variable. I think I will stop at this point. Thank you.